Voyager 1 has been flying for over 46 years. It is the fastest object humanity has ever built, and it is still inside our solar system. At its current speed, reaching the nearest star takes 73,000 years. We haven't left. We have barely moved. Today we cover why the math keeps saying no, why every engine concept breaks down at a different point, and why the engineers who study this problem say the real obstacle isn't technology. If you want more missions like this one, subscribe and hit like. It keeps us going. Strap in. We begin. Picture the fastest thing humans have ever launched into space. A machine the size of a compact car, spinning through the dark at 38,000 miles per hour. It has been flying since 1977. Every single day, it covers a distance greater than the entire diameter of Earth. And right now, as you listen to this, it is still inside our solar system. That machine is Voyager 1. Engineers at NASA track it daily. They know its exact position, its speed, its temperature. They send it commands and wait. The signal travels at the speed of light and still takes over 22 hours to arrive one way. That gap alone should tell you something about the scale of what we're dealing with. Voyager 1 launched during the Carter administration. It flew past Jupiter, it flew past Saturn. It kept going straight out into the dark, on a trajectory that would take it further from Earth than any human object in history. Mission planners celebrated each milestone. The press called it humanity's greatest journey. And they were right. Every word of that was accurate. And yet, the nearest star system to ours, Alpha Centauri, sits roughly 4.2 light-years away. A light-year is the distance light covers in a full year, traveling at 670 million miles per hour. At Voyager 1's current speed, reaching that star system would take approximately 73,000 years, longer than modern human civilization has existed, longer than the last ice age, longer than every recorded war, every empire, every language spoken on Earth, stacked end to end, multiplied many times over. Here is the part that makes engineers go quiet. Voyager 1 is considered a success. It is the gold standard of deep space missions. There is no faster uncrewed probe currently in operation, and 73,000 years is its answer to the nearest possible destination. So the question this entire journey is built around isn't whether we can go faster. We know we need to. The question is what exactly is stopping us, and how many separate walls stand between where Voyager 1 sits right now and a true departure from this solar system. There are more walls than most people expect. Some are physics, some are chemistry, some are engineering, some are money, some are time itself, and a few are problems that don't even have names yet, because no spacecraft has ever survived long enough to encounter them. In 1979, mission planners knew Voyager 1 would eventually leave the region of space dominated by our star's solar wind. They called that boundary the heliopause. For decades it was theoretical, a calculated line on a map no instrument had ever touched. Then, in 2012, Voyager 1 crossed it. Instruments on board detected a sudden shift. The solar wind pressure dropped. The density of charged particles changed. The magnetic field orientation rotated. Scientists confirmed the crossing after months of analysis. The headlines read, "Humanity's first spacecraft exits the solar system." Except the Oort cloud, the vast frozen shell of debris that forms the true gravitational boundary of our star's influence, begins far beyond that point. And it extends so far outward that Voyager 1 won't reach its inner edge for another 300 years. It won't clear the outer edge for another 30,000. We are nowhere near gone, and the reason why goes much deeper than distance. It starts with a piece of mathematics written in 1893 that no rocket design has ever escaped. That equation is where this story truly begins. Ask a planetary scientist where the solar system ends, and ask a spacecraft engineer the same question, and you will get two completely different answers. Both are correct. And the gap between them is one of the most important distances in the history of exploration. The disagreement matters because it changes how we measure progress. If the solar system ends at the heliopause, Voyager 1 crossed it over a decade ago. If it ends at the outer boundary of the Oort cloud, no spacecraft launched by humanity has come anywhere close. and none will for tens of thousands of years. So let's set the waypoints clearly, because this mission brief requires precision. The first boundary is the termination shock. This is where our star's solar wind, a constant stream of charged particles blasting outward in all directions, starts losing the fight against interstellar pressure. The particles slow down sharply. They bunch up. The region feels turbulent if you're an instrument designed to measure particle flow. Voyager One crossed this boundary around 2004, roughly 84 astronomical units from our star. 1 astronomical unit is the distance from Earth to the center of our solar system, about 93 million miles. So 84 times that distance, already incomprehensible by human standards. Beyond the termination shock lies the heliosheath, a churning, foamy zone where the decelerated solar wind piles up and gets redirected. Voyager 1 spent years crossing it. Scientists had models predicting what instruments would detect inside this region, and the data came back stranger than expected. The heliosheath was thicker in some directions, thinner in others. The boundary of our star's influence turns out to be shaped more like a comet than a sphere, pushed and distorted by the interstellar medium flowing past it. Then comes the heliopause, the actual membrane, confirmed by Voyager 1's instruments in 2012, where solar wind stops entirely and true interstellar medium begins. Particles on the other side originate from ancient stellar explosions across the galaxy. The magnetic field orientation shifts. The radiation environment changes character. Voyager 1 is here right now, in this zone, drifting through territory no human machine had ever sampled before. Planetary scientists often call this the edge. Engineers call it the lobby, because past the heliopause, starting somewhere around 1,000 astronomical units out, the Oort cloud begins, and this structure changes the entire framing of the problem. The Oort cloud is a vast spherical shell of frozen objects, comets, icy debris, ancient material left over from the formation of our solar system. It surrounds everything, in every direction, like a bubble. Its inner edge sits roughly 1,000 to 2,000 astronomical units out. Its outer edge extends somewhere between 20,000 and 100,000 astronomical units. At that outer boundary, the gravitational grip of our star becomes comparable to the gravitational influence of neighboring stars. Objects at that edge are barely ours. To cross the Oort cloud entirely, a spacecraft would need to travel approximately 1 to 2 light years. At Voyager 1's speed, clearing it takes around 30,000 years. And after that, the gap between our solar system and the next one begins. The Hill sphere defines the third boundary, the zone where our star's gravity dominates over the combined pull of the rest of the galaxy. Objects inside the Hill sphere are gravitationally ours. Objects outside belong to the galaxy at large. 3 definitions, 3 different distances, all scientifically valid, and none of them have been reached by anything we have ever built. That failure isn't random. It traces back to a formula so fundamental that every rocket engineer memorizes it before they design a single component. In 1893, a Russian school teacher named Konstantin Tsiolkovsky sat down and worked out the mathematics of how a rocket accelerates in space. He had no computer. He had never seen a working rocket. He derived the equation from first principles, published it years later, and essentially wrote the ceiling on every crewed and uncrewed spacecraft that would ever fly. The equation is elegant. It is also brutal. It says this: the change in velocity a rocket can achieve depends on 2 things: the exhaust velocity of the propellant coming out the back, and the ratio of the rocket's starting mass to its ending mass. Starting mass means the vehicle fully fueled. Ending mass means the empty structure after burning everything. Here is why that ratio destroys mission planners. To go faster, you need more fuel. But fuel has mass. More mass means the rocket needs even more fuel just to accelerate that extra fuel, which adds more mass, which requires more fuel. The spiral compounds on itself. Engineers call it the tyranny of the rocket equation, and that name is earned. A useful comparison: the Saturn V rocket that carried astronauts to the moon stood 363 feet tall. At launch, roughly 85% of its total mass was propellant. The payload delivered to lunar orbit was less than 2% of the vehicle that left the launch pad. 2%. Now scale that problem to interstellar distances. To reach even a fraction of the speed needed for a reasonable interstellar transit time, a chemical rocket would need a fuel-to-payload ratio so extreme that the fuel mass would exceed every object humans have ever manufactured, combined by factors of millions. The math doesn't just get difficult, it becomes geometrically absurd. Chemical propulsion, meaning burning fuel and oxidizer to create exhaust and thrust, operates within hard limits set by chemistry. The energy stored in molecular bonds has a ceiling. The best chemical propellants ever developed, liquid hydrogen burned with liquid oxygen, exhaust gases at roughly 14,000 miles per hour. That is the practical limit of what chemistry can deliver. Voyager One didn't reach its current speed through raw engine thrust alone. It used gravity assists, which we'll get to shortly. But even with those assists, it is traveling at roughly 38,000 miles per hour. Light travels at 670 million miles per hour. Voyager 1 is moving at roughly 0.006% of light speed. To reach the nearest star in a human lifetime, a spacecraft would need to travel at a meaningful fraction of light speed. Even 10% would require capabilities so far beyond chemical propulsion that the rocket equation doesn't just make it difficult. It makes chemical rockets categorically the wrong tool, the way a bicycle is the wrong tool for crossing the ocean. And here is what engineers discovered when they accepted that truth. The alternatives all carry their own versions of the same problem. Every proposed replacement for chemical rockets, nuclear engines, ion drives, solar sails, each one trades the chemistry ceiling for a different kind of wall. Some walls are about energy, some are about structure, some are about time, and some reveal themselves only after decades of deep space travel, in forms that no laboratory test can fully simulate. The first escape attempt came not from building a better engine, but from stealing velocity from the planets themselves. On August 25th, 2012, Voyager 1 crossed a line. Instruments on board registered a sharp drop in the density of solar wind particles. The plasma environment changed character within days. Scientists reviewing the data realized they were looking at readings that matched theoretical predictions for the heliopause, the physical membrane where our star's influence ends and interstellar space begins. It took months of analysis to confirm. The announcement came in 2013. Humanity had touched interstellar space. Now, what does that boundary actually consist of? Because calling it an edge suggests a clean line, like a wall you pass through. The heliopause is more complex, and understanding its structure explains a great deal about why crossing it is significant, but not sufficient. Our star continuously emits the solar wind, streams of charged particles, mostly protons and electrons, moving outward at speeds between 200 and 500 miles per second. This wind fills an enormous bubble around our solar system, called the heliosphere. Every planet, every moon, every asteroid, every comet we have ever visited sits inside this bubble. The heliosphere is our star's atmosphere, extended across billions of miles. Beyond the heliosphere lies the interstellar medium. This is ancient gas and dust, filling the space between star systems. It moves, it has its own pressure, its own magnetic field, its own particle density. Where the two regions meet, the solar wind and the interstellar medium press against each other, like two rivers colliding. Neither fully wins. The boundary flexes, breathes, distorts seasonally as our star's output varies. Voyager 1's instruments measured several simultaneous changes when crossing this region. The solar wind particle count dropped by a factor of roughly 1,000 within a period of days. Galactic cosmic rays, high-energy particles originating from supernovae across the galaxy, increased sharply. The magnetic field shifted direction. Scientists had predicted most of these changes, but the speed and sharpness of the transition surprised them. The plasma wave instrument, which measures oscillations in charged particle environments, provided the most dramatic confirmation. It detected vibrations in the surrounding plasma, consistent with interstellar density, proving Voyager 1 was swimming in material that originated outside our solar system. Here is the part that carries the most operational weight for any future mission. The heliosphere provides a kind of shielding. Our star's magnetic influence deflects and slows a significant fraction of galactic cosmic rays before they reach the inner solar system. Humans and spacecraft inside the heliosphere receive some protection from the most energetic particles in the galaxy. Outside the heliopause, that shielding disappears entirely. The radiation environment on the other side is measurably harsher. Any crewed mission transiting this region faces a sudden step increase in cancer risk and electronics degradation. Voyager One survived because it carries no humans, and its instruments were designed for decades of operation in harsh conditions. A crewed vehicle would need dedicated shielding for this transition, adding mass, which circles back immediately to the rocket equation. The heliopause is a physical reality, confirmed by direct measurement, and crossing it revealed the next layer of the problem, rather than resolving anything. Past this boundary, the scale shifts again. Distances between stars are measured in light years. Voyager 1, traveling at its current speed, covers roughly 1 light year every 17,000 years. The structure waiting further out, the Oort cloud, will test instruments, power systems, and communication links in ways that make the heliopause crossing look like a routine waypoint. Strip every spacecraft ever built down to its operating principle, and you find the same mechanism. Hot gas exits through a nozzle. The rocket moves in the opposite direction. Every crewed mission in history, every planetary probe, every satellite. Same principle. The performance of that mechanism depends entirely on how fast the exhaust moves. Engineers call this the specific impulse. Higher exhaust velocity means more push per pound of fuel burned, and the limit on exhaust velocity is set by chemistry. When you burn a propellant, you're breaking and forming chemical bonds. That process releases energy. The energy heats the combustion gases. Hot gases expand and accelerate out the nozzle. The maximum temperature those gases can reach is governed by the energy stored in the molecular bonds of the propellant. Change the propellant, and you change the ceiling. But every chemical combination ever tested hits a ceiling far below what interstellar travel requires. The best operational chemical propellant combination is liquid hydrogen burned with liquid oxygen. Engines using this mixture have specific impulse values around 450 seconds, a technical unit that translates to exhaust velocities near 14,000 miles per hour. Scaling up engine size doesn't help. Running engines longer doesn't help. Adding more propellant tanks, as the rocket equation showed, makes the mass problem worse. The chemistry is the ceiling, and the ceiling is firm. Here is a direct comparison to frame the gap. Voyager 1's current speed, approximately 38,000 miles per hour. Speed needed to cross to Alpha Centauri within 100 years, roughly 28 million miles per hour, or about 4% of light speed. Speed of light? 670 million miles per hour. Chemical propulsion gets you to a number that doesn't meaningfully appear in that comparison. The gap between Voyager 1 and a practical interstellar crossing is larger than the gap between a person walking and a commercial airplane. Engineers understood this constraint by the early 1960s. The question shifted from how do we burn better chemicals to how do we replace the combustion process entirely. Several answers emerged, and each one addressed a specific part of the ceiling, while introducing a different constraint that engineers then spent decades trying to solve. Ion drives, for instance, use electric fields to accelerate charged particles to exhaust velocities many times higher than chemical combustion. The Dawn spacecraft, which visited the asteroid belt, used ion propulsion. Exhaust velocity climbs. Thrust, however, drops dramatically. An ion engine produces roughly the force of a sheet of paper resting on a table. At that thrust level, reaching meaningful interstellar velocities requires either enormous amounts of time or a power source far beyond anything currently operational in space. Nuclear thermal engines burn a propellant by heating it through a reactor rather than combustion. The exhaust velocity doubles compared to chemical engines. Still nowhere near interstellar requirements, but the improvement is real. Each of these transitions improves one variable, while another becomes the new bottleneck. The pattern repeats at every level of propulsion technology. Fix the chemistry problem, and a power problem appears. Fix the power problem, and a mass problem returns. Fix the mass problem, and a time problem surfaces. Every wall cleared reveals the next one standing behind it. One of the first walls engineers cleared, not through better engines, but through borrowed physics, produced the trajectory that got Voyager 1 as far as it has traveled. And the window to use that trick opened only once in 175 years. In the late 1960s, a graduate student named Gary Flandreau at the Jet Propulsion Laboratory was working on orbital mechanics calculations. He was looking at the positions of the outer planets projected forward in time, and he found something that happens once every 175 years. Jupiter, Saturn, Uranus, and Neptune were approaching an alignment, a specific geometric arrangement where a spacecraft could fly past one planet, use its gravitational field to gain speed and redirect trajectory, then slingshot toward the next planet in sequence, repeating the boost multiple times across a single continuous journey. The alignment window opened in the late 1970s and closed within a few years. NASA moved fast. The result was the Voyager program. Here is how a gravity assist actually works, because the mechanics are less obvious than they appear. When a spacecraft approaches a massive planet, gravity pulls it inward. The spacecraft accelerates. It swings around the planet, and the planet's gravity continues pulling. If the trajectory is calculated correctly, the spacecraft exits the encounter moving faster than it entered, and in a new direction aimed at the next destination. Energy is conserved. The spacecraft gains kinetic energy, but the planet loses an imperceptibly tiny amount of orbital momentum. A planet the mass of Jupiter loses so little that measuring the effect requires instruments beyond current capability. For practical purposes, the spacecraft gets a free velocity boost. Voyager 1 used Jupiter's gravity to accelerate towards Saturn. Saturn's gravity redirected it further out. The final trajectory sent it on a path angled above the ecliptic plane, the flat disk where most planets orbit, on a course heading toward interstellar space. The speed gained through these assists was decisive. Without them, Voyager 1 would have taken decades longer to reach its current position. The gravity assist technique is the single most efficient velocity gain available to spacecraft using conventional propulsion. The problem is geometry. Planetary alignments of this quality are rare. The one Flandreau identified recurs roughly every 175 years. The next comparable window for reaching the outer solar system won't open until sometime in the 22nd century. Any interstellar precursor mission planned in the coming decades cannot rely on that technique for the outer leg. Beyond the alignment problem, gravity assists have diminishing returns at the scales interstellar travel demands. The boosts available from solar system planets add thousands of miles per hour to a spacecraft's velocity. Interstellar missions require gains measured in millions of miles per hour. Gravity assists from our star, performing a close solar flyby to pick up speed before heading outward, have been proposed. A spacecraft flying close enough to our star's surface could theoretically reach speeds 5 to 10 times Voyager 1's velocity. Engineers call this an Oberth maneuver, using a rocket burn at maximum gravitational depth for maximum efficiency. Even that improvement leaves the spacecraft traveling at a small fraction of a percent of light speed. Meaningful, but still orders of magnitude short of interstellar requirements. So the gravity assist era established the frontier. Voyager 1's position today is the direct result of Flandreau's calculation, and that once-in-a-lifetime alignment, everything beyond that position requires something categorically different. And the first serious attempt at something different involved nuclear weapons. Imagine a shell surrounding our entire solar system, a hollow sphere packed with trillions of frozen objects, ranging from the size of a house to the size of a small city. Comets, ice, ancient debris left over from the formation of our star and its planets. This shell sits so far from the center of our solar system that sunlight reaching its inner edge is 10,000 times dimmer than what reaches Earth. This is the Oort cloud, and Voyager 1 won't reach its inner edge for approximately 300 years. The Oort cloud has never been directly observed. No telescope has resolved individual objects within it. Its existence is confirmed through a different method, the long-period comets that occasionally fall inward toward the inner solar system. These objects come from all directions, from all points on the celestial sphere, suggesting their source is a surrounding shell rather than a disk. Their orbital periods, the time they take to complete one trip around our star, span hundreds of thousands to millions of years. The math of those orbits points to an origin region matching the Oort cloud's predicted location. Scientists are confident the structure exists. The exact density and boundaries remain in the category of well-supported inference, not direct measurement. Here is the scale that matters for this mission brief. The heliopause, the boundary Voyager One crossed in 2012, and which generated global headlines about leaving the solar system, sits roughly 120 astronomical units from the center of our system. The inner edge of the Oort cloud begins somewhere around 2,000 astronomical units. The outer edge extends to somewhere between 20,000 and 100,000 astronomical units. 1 light-year is approximately 63,000 astronomical units. The Oort cloud spans at its outer reaches approximately 1 to 2 light-years in radius. Our solar system, defined by the gravitational boundary that keeps these objects loosely bound to our star, extends 1 to 2 light-years in every direction. The nearest star system, Alpha Centauri, is 4.2 light-years away. So the journey between our solar system and the nearest neighboring one covers a gap of roughly 2 to 3 light-years after clearing the Oort cloud. And clearing the Oort cloud alone takes, at Voyager 1's velocity, about 30,000 years. This reframes the entire conversation about interstellar travel. Every milestone celebrated so far, every probe launched, every record broken, has occurred within a tiny fraction of the distance to the true gravitational edge of our home system. We have not sampled the Oort cloud. We have not crossed it. We have not exited it. We have barely confirmed it exists through indirect observation. Mission planners who think seriously about interstellar probes must contend with this structure as the first sustained transit challenge. A spacecraft crossing the Oort cloud would travel for millennia through a region with no planetary gravity assists, no solar power, no quick communication window. Every system on board must function flawlessly through that entire transit. No spacecraft in history has been designed for that requirement. The longevity records that currently exist are measured in decades. What gets even harder to process is this: the engineering proposals that could realistically shorten that transit time, or require energy sources and technologies that exist, so far, only on paper or in early testing phases. The most dramatic of those proposals was designed not by engineers dreaming of the future, but by a team working in the 1950s who were given access to nuclear weapons and told to think big. In 1958, a group of physicists at General Atomics in San Diego began working on a spacecraft propulsion concept that no other engineering team has matched for raw performance potential, before or since. The concept was called Project Orion, and it worked by detonating nuclear bombs behind the spacecraft. This is confirmed history, documented in declassified government records and published research. A team that included physicist Freeman Dyson designed a vehicle with a massive metal pusher plate at its rear, suspended on shock absorbers. Nuclear devices roughly the size and yield of early tactical warheads would be ejected behind the plate one at a time and detonated. Each detonation would slam a pulse of expanding plasma into the plate. The plate would absorb the impact and transfer momentum to the spacecraft through the shock absorber system. Repeat the cycle hundreds or thousands of times, and the spacecraft accelerates. The performance numbers were extraordinary by any measure of propulsion physics. A large Orion vehicle, the kind the team called the Interstellar version, could theoretically accelerate to between 3 and 10% of light speed. At 3%, a trip to Alpha Centauri takes roughly 140 years. At 10%, roughly 40 years. These are numbers that human civilization could, in principle, organize around. A mission launched by one generation, arrived at by descendants. The engineering was credible. The team built small chemical explosive models to test the pusher plate dynamics. The models flew, the shock absorption system worked. The fundamental concept held up to scrutiny from some of the sharpest physicists of the 20th century. Dyson himself believed the interstellar version was achievable within the technology base of the 1960s, given sufficient funding and political will. The project was cancelled in 1965. The direct cause was the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. Orion required exactly those detonations. The legal framework that helped reduce Cold War nuclear escalation also eliminated the propulsion system that came closest to making interstellar transit physically credible. No replacement has matched Orion's performance potential in the 60 years since. Some researchers have proposed modern variants using smaller, cleaner nuclear pulse devices. The nuclear physics remains consistent with the original analysis. The political and treaty barriers remain equally consistent. Project Orion didn't fail because of bad engineering. The engineering worked. It failed because the most capable propulsion concept humanity has ever seriously designed required detonating nuclear weapons in space, and the international community decided that was unacceptable. That decision was understandable. The consequence is that the fastest credible vehicle humans ever designed sits permanently in the category of abandoned proposals. Every alternative that followed had to work within tighter constraints, and each one found a different wall waiting on the other side of the engineering. The next constraint isn't explosive, it's arithmetic, and the numbers it produces are so extreme they reframe the entire definition of what building a spacecraft means. Engineers have a way of making an impossible problem visible. They run the numbers. They don't argue about whether something feels achievable. They calculate the mass ratio, check the result, and let the arithmetic describe what the universe is actually willing to allow. For interstellar travel using any propulsion system governed by the rocket equation, the arithmetic delivers a consistent verdict. Start with a target. Say a spacecraft needs to reach 10% of light speed to make a transit to the nearest star system in a human-relevant time frame, roughly 40 years one way. Ignore deceleration for now. That problem comes later. Focus purely on acceleration. For chemical propulsion, the mass ratio required to reach 10% of light speed is so astronomically large that the fuel mass would exceed the mass of the observable universe by a substantial factor. Chemical propulsion is categorically eliminated at this velocity target. For nuclear thermal propulsion, which doubles the exhaust velocity of the best chemical engines, the mass ratio remains completely impractical, better, but eliminated by the same arithmetic. For a more advanced nuclear pulse drive with exhaust velocities approaching 1% of light speed, the mass ratio starts becoming physically conceivable. But a spacecraft designed to carry 1 ton of useful payload to 10% of light speed would need a fuel mass thousands of times greater than that payload. The vehicle launched from Earth's orbit would need to mass many thousands of tons for a payload a person could lift. Scaling up the payload makes everything worse. The rocket equation compounds. Every kilogram added to the useful payload demands exponentially more fuel. Here is a physical comparison that holds the scale. The International Space Station masses roughly 420 tons in orbit. Building it required over 30 rocket launches across more than a decade. An interstellar mission using nuclear pulse propulsion, aimed at 10% of light speed, carrying a crew and life support for a multi-decade journey, would require a vehicle massing many thousands of times the space station. Assembling that structure in orbit, fueling it, and launching it is an industrial undertaking that dwarfs every construction project in human history combined. This is why the engineering community largely redirected focus toward 2 alternative strategies. The first, dramatically reduce the payload. If you don't need humans or large instruments, if you can send something the mass of a postage stamp, the mass ratios become conceivable. This approach leads directly to concepts like laser-driven light sails. The second, find a propulsion system that operates outside the rocket equation entirely, meaning one that doesn't carry its own fuel. A system powered by an external source that does the pushing from a fixed location. Both strategies have serious engineering proposals attached to them. Both also carry their own category of wall. And before any of those walls appear, a more immediate physical problem challenges every fast-moving spacecraft the moment it leaves the protective bubble of our heliosphere and enters the thin gas and dust of interstellar space. At high speed, even emptiness becomes a weapon. Interstellar space is close to empty. The density of gas and dust between star systems is roughly 1 atom per cubic centimeter in some regions. For comparison, the air at sea level on Earth contains roughly 27 million trillion atoms per cubic centimeter. Interstellar space is by any measure a near-perfect vacuum, and at a significant fraction of light speed, it destroys spacecraft. Here is the physics. When you move through a medium, even an extremely thin one, particles in that medium hit your leading surface. At ordinary speeds, the impact energy per particle is negligible, but kinetic energy scales with the square of velocity. Double the speed and the impact energy quadruples. Triple it and the impact energy increases ninefold. At 10% of light speed, each hydrogen atom in the interstellar medium that strikes a spacecraft's forward surface carries the impact energy of a high-velocity rifle round, scaled to atomic size. Multiply by the number of atoms encountered per second over interstellar distances, and the accumulated damage becomes structural. A team of researchers published analysis on this problem in 2019, specifically examining the breakthrough starshot concept, which aims to send a small probe at 20% of light speed. Their calculations showed that even with optimized shielding materials, erosion from interstellar hydrogen atoms and dust grains would progressively ablate, meaning vaporize and strip away, the forward surface of any probe traveling at that velocity. Over a 4-light-year transit, the depth of material removed from an unprotected surface could reach several centimeters. For a probe designed to be the size of a postage stamp, several centimeters of erosion means total destruction. Proposed solutions include angling the spacecraft so the erosion hits the edges rather than critical components, designing a sacrificial ablation shield on the forward surface, or navigating around denser dust clouds using trajectory adjustments sent from Earth. All three approaches reduce the problem. None eliminate it. For larger crewed vehicles traveling at lower fractions of light speed, the erosion rate per second is lower. The transit time is longer. The cumulative damage may reach similar levels. The material challenge is the same. Build a forward surface that can withstand decades of high-velocity particle bombardment without losing structural integrity. No material tested in any laboratory environment today meets that specification for multi-decade interstellar transits at multi-percent light speed. The interstellar medium is thin enough that we built entire theories about it by assuming it was effectively empty. The faster a spacecraft travels, the more that assumption fails. And the erosion problem compounds with a separate challenge that the breakthrough starshot team has studied in detail. The laser array capable of pushing a light sail to 20% of light speed would also, by the physics of photon pressure, require engineering that has no precedent in human construction history. That is where the journey goes next. In 2016, a group of scientists and investors announced a project called Breakthrough Starshot. The concept: use a ground-based laser array to push a gram-scale spacecraft, essentially a tiny sail with a microchip payload, to 20% of light speed. At that speed, it would reach the Alpha Centauri system in roughly 20 years. The science is real. Photons carry momentum. When they strike a reflective surface, they transfer that momentum. A sufficiently large, sufficiently powerful laser, aimed at a sufficiently light sail, can push it to extraordinary velocities. Breakthrough Starshot's engineering documents are public. The numbers inside them are serious. The laser array required to push a gram-scale sail to 20% of light speed would need to produce roughly 100 gigawatts of power for a burst of approximately 10 minutes. 100 gigawatts is roughly equivalent to the total electrical generating capacity of the United Kingdom, fired as a focused beam. The array would consist of thousands of individual laser units, synchronized to focus on a sail roughly tens of meters wide, made of material nanometers thick. The sail material must be reflective enough to absorb minimal laser energy, thin enough to be nearly massless, and strong enough to survive the acceleration forces, which would reach thousands of times Earth's gravity during the boost phase. The microchip payload on the sail needs a camera, a communication system capable of transmitting data across 4.2 light-years, and enough power to operate. Total mass allowed for the entire payload, roughly 1 gram. Currently, no technology meets any of these specifications in deployable form. The team identified the key engineering milestones honestly in their published documents. Laser coherence at the required scale is unsolved. Sail materials with the required reflectivity, thinness, and strength don't exist. Pointing accuracy to keep a laser focused on a sail at interstellar distances requires precision beyond current capability. The communication system for a gram-scale transmitter reaching Earth from 4 light-years has no working prototype. The project team describes the timeline as a multi-decade engineering challenge rather than a near-term launch. The physics is confirmed. The hardware doesn't exist. If the engineering problems are solved and a probe launches, the 20-year transit still carries the erosion problem from the previous chapter. The probe's forward surface will encounter interstellar dust at 20% of light speed continuously for the entire crossing. And after 20 years of flight, when the probe reaches the Alpha Centauri system, it will fly through at 20% of light speed with no way to slow down. Because stopping is a separate problem, and it may be harder than accelerating. Every interstellar mission concept that involves actually studying a destination rather than flying past it at a fraction of light speed hits this wall immediately. Accelerating a spacecraft is a solved concept in principle. Apply thrust, gain velocity. The engineering is difficult, but the physics is unambiguous. Deceleration requires the same thing in reverse. Apply thrust opposing the direction of motion. Here is why that symmetry is catastrophic for mission planners. To slow down from a significant fraction of light speed, you need fuel. The rocket equation applies exactly as it did for acceleration. The deceleration burn requires its own fuel load, proportional to the spacecraft's mass and the velocity change needed. But the fuel for deceleration must travel with the spacecraft during the entire acceleration phase. That extra fuel mass must be accelerated from rest to full cruising speed and then decelerated. The rocket equation compounds both ways. A spacecraft designed to accelerate to 10% of light speed and then decelerate to rest at the destination, carrying enough fuel for the full round trip, requires a mass ratio that makes the one-way acceleration case look manageable. For chemical propulsion, the required fuel mass is effectively infinite. For nuclear pulse propulsion, the ratios become truly enormous. Breakthrough Starshot acknowledges this directly. The probe they propose flying through the Alpha Centauri system at 20% of light speed will complete that flyby in hours. It cannot stop. Scientists would have hours to collect data across 4.2 light-years of transit, then lose contact as the probe continues outward into deep space. An interstellar mission that cannot break at the destination delivers a fraction of the scientific value of a mission that can orbit or land. Several proposed solutions exist in the engineering literature. One involves using the magnetic field of the destination star to brake against a technique called magnetic sailing. A superconducting loop generates a magnetic field that interacts with the stellar wind of the target star, creating drag. No materials currently exist with the required superconducting properties at the temperatures encountered in space. Another involves a laser system at the destination, built perhaps by self-replicating machines sent ahead, that fires at the incoming probe's sail in reverse to decelerate it. That proposal adds a layer of complexity requiring prior deployment of infrastructure at a destination humanity has never visited. A third concept proposes staged missions. An initial probe flies through and collects data, while a second, slower mission uses the first probe's data to plan a braking approach using the destination star's own gravity in a complex orbital insertion. All three are serious proposals. All three have engineering prerequisites that are currently unmet. The deceleration problem is the quiet filter that eliminates mission concepts that otherwise look achievable. An interstellar mission that cannot stop is a flyby. A flyby at 20% of light speed yields hours of observations. That is the current practical ceiling. The engine concept that would have changed this calculation most significantly was tested in the Nevada desert in the 1960s, worked exactly as designed, and then the program was cancelled without a replacement. Between 1955 and 1972, the United States ran a program called Project Nerva. The full name was Nuclear Engine for Rocket Vehicle Application. Engineers built and ground-tested a series of nuclear thermal rocket engines. The engines worked. Here is how a nuclear thermal engine operates. A nuclear fission reactor sits at the core of the engine. Liquid hydrogen propellant flows through or around the reactor, absorbs heat from the nuclear reactions, and expands rapidly through a nozzle. The hydrogen itself is not burned. It is heated. The heated hydrogen exits the nozzle at exhaust velocities roughly twice as high as the best chemical engines. Twice the exhaust velocity means, by the rocket equation, a dramatically better mass ratio for the same velocity change. A nuclear thermal rocket can achieve the same mission with roughly half the propellant mass of a comparable chemical rocket. For missions to Mars, this is enormously significant. Mission planners in the 1960s calculated that a nuclear thermal propulsion system could cut transit time to Mars roughly in half and reduce the propellant mass requirements substantially. The NERVA program ran 20 ground tests on actual nuclear rocket engines at a Nevada test site. The most capable engine, called the Pewee class, produced about 55,000 pounds of thrust while running at a reactor temperature of around 4,300 degrees Fahrenheit. It ran for extended test durations. It performed as designed. NASA planned to use NERVA engines for a crewed Mars mission in the 1980s. The mission design was serious enough that engineers began specifying vehicle components. In 1972, the program was cancelled. Budget priorities shifted. The crewed Mars mission was cancelled with it. The engines were archived. The test sites were decommissioned. No nuclear thermal rocket has flown in space since. The technology did not fail. The physics remains valid. Exhaust velocity figures from the NERVA tests are still cited in modern mission architecture documents when comparing propulsion options. Several space agencies and private companies have announced nuclear thermal propulsion development programs in recent years. NASA awarded development contracts for a nuclear thermal engine concept aimed at a Mars mission demonstration. The technical approach builds on NERVA heritage data. For interstellar travel, nuclear thermal propulsion is a step forward, but still short of the required performance by many orders of magnitude. The exhaust velocity improvement is real. The velocity achievable by a nuclear thermal spacecraft still represents a fraction of a percent of light speed. The gap to interstellar transit speeds remains vast. Where nuclear thermal propulsion becomes relevant for interstellar ambitions is as a high-efficiency workhorse for the inner solar system, allowing missions to build up speed through repeated gravity assists or staged acceleration sequences before transitioning to a more exotic drive for the interstellar leg. The engine that could handle the interstellar leg is one that doesn't carry fuel at all in the conventional sense, one that annihilates matter itself. But producing that fuel is a problem so large, it requires a completely different accounting of what feasible means. Voyager One is currently over 14 billion miles from Earth. A signal sent from Mission Control at the Jet Propulsion Laboratory travels at the speed of light and takes over 22 hours to arrive. The response, if Voyager 1 systems generate one, takes another 22 hours to return. Total round-trip communication delay, over 44 hours. For context, in the time it takes a command sent today to receive a confirmation, a person can fly from Los Angeles to Tokyo and back 4 times. Engineers at the Jet Propulsion Laboratory who work with Voyager 1 described the experience in practical terms. Commands are planned days in advance. Sequences are uploaded in batches. Real-time control is impossible. If something goes wrong on board, the spacecraft must handle it autonomously, or wait 44 hours for a human response while the situation develops. Voyager 1's distance will only grow. Any spacecraft traveling toward interstellar space will experience increasing communication delays, until at some point the delay becomes so long that the concept of mission control as a functional oversight team dissolves entirely. A probe at the Alpha Centauri system would have a one-way communication delay of over 4 years. Ask a question, wait 4 years for the answer. An autonomous system capable of operating for decades without human direction. Capable of making decisions about scientific priorities, equipment failures, and navigation adjustments is a software and artificial intelligence challenge that has no current solution in the form required. For crewed missions, the communication delay presents a different kind of problem. At interstellar distances, Earth cannot function as a decision-making authority. The crew becomes entirely self-governing, medically, mechanically, politically. Every crewed interstellar mission concept that has been seriously studied identifies crew autonomy as one of the most challenging non-engineering requirements. Earthbound support becomes advisory at best. Any emergency requiring Earth consultation would resolve itself, one way or another, years before a response could arrive. The Deep Space Network The system of large radio antennas NASA uses to communicate with distant probes can barely resolve Voyager One's signal today. The probe's transmitter puts out roughly 22 watts of power, the equivalent of a refrigerator light bulb. By the time that signal crosses 14 billion miles and reaches Earth, it arrives at power levels so faint that the receiving dish must be among the most sensitive radio receivers ever built to detect it. A probe at interstellar distances, transmitting the same power, would produce a signal thousands of times fainter than current deep space network capability can detect. The communication architecture for a true interstellar probe requires either a dramatically more powerful onboard transmitter, which adds mass, or a fundamentally more sensitive receiving system on Earth, which requires a radio telescope array larger than any currently existing. Both are solvable in principle. Neither is built. The communication problem is one of those constraints that remains mostly invisible in mission planning discussions because it feels secondary to propulsion. But a probe that arrives at its destination and cannot send data back has accomplished nothing observable. And the data it would need to send back across 4 light years is the product of instruments powered by a system that begins failing long before the probe ever reaches the edge of our solar system. Every propulsion system discussed so far stores energy in some form and releases it as thrust, chemical bonds, nuclear fission, photon pressure from external lasers. Each represents a point on a spectrum of energy density measured in how much energy a given mass of fuel can release. At the top of that spectrum, above every other option physically allowed by the laws of nature, sits antimatter. When a particle of matter meets its antimatter counterpart, both annihilate completely. Every kilogram of mass converts to energy according to Einstein's equation. The energy released per kilogram of antimatter, annihilated with a kilogram of ordinary matter, is roughly 10 billion times greater than the energy released by burning the same kilogram of chemical propellant. It is roughly 1,000 times greater than the energy released by nuclear fission. A kilogram of antimatter fuel, in principle, releases more energy than the most powerful nuclear weapon ever detonated. Annihilation is total. No waste products carry away unused energy as unburned fuel or residual heat in the reactor structure. The conversion is complete. For propulsion, the concept is straightforward. Combine matter and antimatter in a controlled reaction chamber. Direct the annihilation products through a magnetic nozzle. Generate thrust. An antimatter rocket using proton-antiproton annihilation could theoretically achieve exhaust velocities approaching the speed of light, giving it the best possible specific impulse of any fuel-based propulsion system. A spacecraft with those performance numbers could realistically reach meaningful fractions of light speed with manageable mass ratios. The problem is production. Antimatter does not exist in usable quantities in the natural world accessible to us. It must be manufactured in particle accelerators, where high-energy collisions occasionally produce antiparticles. The rate of production is extraordinarily low. The world's most powerful particle accelerator at CERN in Switzerland produces roughly 10 nanograms of antiprotons per year at maximum output. 10 nanograms is approximately 1/10,000,000th of a gram. Estimates for the antimatter required to accelerate a crude interstellar vehicle to a meaningful fraction of light speed range from tens to hundreds of grams at minimum, assuming extremely efficient magnetic nozzle designs. At current production rates, gathering that quantity would take millions to billions of years. Scaling up antimatter production would require a dedicated accelerator facility, consuming energy at a scale comparable to entire national power grids, running continuously for timescales far beyond any current planning horizon. Researchers are studying more efficient production pathways. Some theoretical approaches involve capturing antiparticles naturally produced by cosmic ray collisions in Earth's upper atmosphere or near radiation belts around other planets. The quantities remain tiny compared to mission requirements. Antimatter propulsion sits in a category that physicists describe as theoretically optimal and practically inaccessible with current or near-future technology. The energy is real, the physics works. The fuel cannot be gathered at scale by any method humans currently know. And while engineers wrestle with how to produce antimatter, the probes that have already launched are quietly running out of a different kind of power entirely, one that has nothing to do with propulsion. Voyager One is running out of power. slowly, steadily, irreversibly. The probe doesn't use solar panels. At its current distance, sunlight is so faint that solar panels large enough to generate useful electricity would be impractical. Instead, Voyager One carries radioisotope thermoelectric generators. These devices use the heat released by the natural radioactive decay of plutonium-238 to generate electricity through thermoelectric converters. When Voyager One launched in 1977, its generators produced roughly 470 watts of electricity. That number declines at a fixed rate, roughly 4 watts per year, as the plutonium fuel depletes and the thermoelectric materials degrade. By 2024, output had dropped to below 150 watts. Engineers have been systematically shutting down instruments to keep the remaining science instruments functional. Heaters for some systems have been turned off. The spacecraft is operating in a reduced capacity that grows more reduced with each passing year. Current projections suggest that sometime in the late 2020s, Voyager One's power output will drop below the minimum threshold to operate any science instruments. It will still exist as a physical object. It will still be moving through interstellar space, but it will transmit nothing useful. A spacecraft that launched nearly 50 years ago and has already crossed into interstellar space is days away from science silence, in mission planning terms. For any future interstellar probe, power architecture is a foundational design constraint, not an afterthought. The probe must generate electricity for the entire transit duration, potentially thousands of years for a slow mission, decades for a fast one. Radioisotope thermoelectric generators have a fixed lifespan tied to isotope half-life and material degradation. Plutonium-238 has a half-life of roughly 88 years, meaning power output halves every 88 years. A probe designed for a 40-year transit to Alpha Centauri at significant fractions of light speed might arrive with functional power systems. A probe designed for a slower 1,000-year transit using near-term propulsion technology would arrive with generators producing a tiny fraction of their launch power. Nuclear fission reactors represent one alternative for longer missions. A small fission reactor could produce power for much longer timescales, limited by fuel quantity rather than isotope decay rate. NASA and other agencies have tested small space nuclear reactors. The technology exists in early form. The deeper problem for very long missions is material degradation, independent of power source. Electronics, seals, structural components, and moving parts degrade over timescales of decades. A probe designed to function for thousands of years must use materials and architectures with no heritage, no test data, and no engineering precedent. Voyager One's impending silence is the clearest demonstration in real time of how quickly a spacecraft's useful operational life ends relative to the distances it needs to cover. And beyond the power problem, traveling fast through interstellar space introduces a radiation environment so hostile that it threatens both electronics and any living crew in ways that make Voyager One's challenges look straightforward. Strip a rocket engine down to its most fundamental requirement. It needs to expel mass backward. The faster that mass leaves, the better the engine performs. Exhaust velocity is everything. Now push that logic to its absolute physical limit. The fastest thing that can exit a rocket nozzle is light. Photons travel at the speed of light by definition. A rocket that expels photons as exhaust would have the highest possible exhaust velocity allowed by physics. Engineers call this concept the photon rocket. The math that results from plugging photon exhaust velocity into the rocket equation produces performance numbers that no other fuel-based propulsion system can match. A photon rocket could, in principle, achieve any velocity below the speed of light given sufficient energy and time. The mass ratios are extreme but physically possible, unlike the ratios that emerge from chemical or even nuclear propulsion at similar velocity targets. The problem is efficiency. Converting stored energy into photon exhaust with perfect efficiency is impossible in practice. Every conversion step loses energy. A photon rocket would require a power source capable of converting fuel mass or stored energy into a directed beam of photons with extremely high efficiency. The most plausible candidates involve matter-antimatter annihilation, directed into a photon beam, which circles back to the antimatter production problem from the previous chapter. Even a photon rocket operating at high efficiency would require staggering quantities of energy. Accelerating a crewed vehicle to 10% of light speed using directed photon exhaust demands a power output sustained over months or years that exceeds any energy infrastructure humans have ever built. The directed energy approach from breakthrough Starshot sidesteps the onboard fuel problem by placing the energy source on the ground, pointing a laser at the sail. This solves the mass ratio problem for the spacecraft itself, but transfers the engineering challenge entirely to the ground infrastructure. A 100 gigawatt laser array is a ground-based photon rocket that pushes the spacecraft rather than powering one on board. Both approaches, onboard photon drives and externally directed energy, run into the same physical boundary from different directions. The energy required to push mass to meaningful interstellar velocities is so large that the infrastructure to generate it is a civilizational scale engineering project, far beyond what any single nation or even current international cooperation could assemble. Researchers at several institutions continue developing directed energy systems on a smaller scale. Laser propulsion experiments have demonstrated the concept works at laboratory scale. The scaling challenge between laboratory demonstration and 100 gigawatts of focused coherent laser energy is the gap between knowing something works and having the industrial capacity to build it at the required scale. The photon rocket and the laser sail are the theoretical ceiling and the near-term engineering attempt at reaching that ceiling. Both are real, both are far from operational, and in the space between what the physics allows and what engineers can currently build, the radiation streaming through interstellar space has a decades-long head start on destroying any probe or crew that attempts the crossing. What that radiation does to electronics and human biology over the timescales interstellar travel demands is the kind of problem that gets quietly set aside in optimistic mission proposals and very loudly surfaced when anyone does the full calculation. Outside the heliosphere, the radiation environment changes character completely. Inside our star's protective bubble, the solar wind and magnetic field deflect a significant fraction of the most energetic particles in the galaxy. The heliosphere is imperfect shielding, but it is shielding. Astronauts on the International Space Station receive radiation doses higher than people on Earth, but the Earth's magnetosphere still provides partial protection. Astronauts on the lunar surface during the Apollo missions faced higher exposure. Each step outward removes a layer of protection. Beyond the heliopause, galactic cosmic rays arrive from every direction with nothing filtering them. These particles are atomic nuclei, mostly protons and heavier nuclei from iron and other elements, accelerated to extreme velocities by stellar explosions across the galaxy. They carry enormous kinetic energy per particle. When one strikes a human cell, it can snap both strands of the DNA helix simultaneously. Standard radiation shielding that works against solar particle events, the kind spacecraft carry today, provides minimal protection against the highest energy cosmic rays. The particles are moving fast enough to punch through meters of metal. Studies on astronauts aboard the International Space Station and modeling work based on Voyager One's particle detectors in interstellar space allow researchers to estimate the dose a crew would receive during an interstellar transit. For a 40-year transit to the nearest star system at 10% of light speed, without dedicated shielding, cumulative radiation exposure would reach levels associated with near-certain fatal cancer development and progressive cognitive decline. Studies on mice exposed to simulated galactic cosmic ray environments showed measurable brain function degradation, including memory impairment and increased anxiety behaviors, after relatively short exposures. The particles cause direct neural damage independent of the cancer risk. For electronics, the challenge is different but equally serious. High-energy cosmic rays cause single-event upsets in computer memory, bit flips, where stored data changes unexpectedly due to particle impact. Modern electronics operating in deep space require radiation-hardened designs that use older, slower manufacturing processes, specifically because newer, smaller transistors are more vulnerable to single-event damage. Over decades of interstellar transit, cumulative electronics damage compounds into systems failure. Proposed shielding solutions include water walls surrounding crew quarters. Since hydrogen in water is reasonably effective at absorbing lower energy particles, and superconducting magnetic shields that deflect charged particles around the crew habitat. The magnetic shield concept requires superconducting loops carrying enormous electrical currents, sustained for the entire mission duration, powered by a reactor system that must itself survive the same radiation environment. No shielding solution currently eliminates galactic cosmic ray exposure to safe levels for long-duration missions. Reduction is achievable. Elimination is not, with current materials. A crewed interstellar mission flying today, using current shielding technology, would deliver a crew to the destination with substantially compromised health and reduced life expectancy compared to people who stayed on Earth. That is the confirmed scientific position. Radiation is a wall that stands between every crewed interstellar concept and the destination. And the engine concept proposed to deal with it by traveling fast enough that transit time stays short. The Bussard ramjet turned out to carry a fatal flaw hidden inside the very interstellar medium it was designed to use as fuel. In 1960, a physicist named Robert Bussard published a proposal that seemed, for a moment, to solve the fuel problem entirely. His concept was elegant. Interstellar space contains hydrogen, sparse hydrogen, but hydrogen spread across unimaginably large volumes. A spacecraft with a large enough electromagnetic scoop could collect that hydrogen as it flew, funnel it into a fusion reactor at the front of the ship, burn it, and exhaust the products behind. The faster the ship moves, the more hydrogen it scoops per second. The more hydrogen it scoops, the more fuel it has. A ramjet that feeds itself from the medium it travels through, requiring no onboard fuel supply beyond the initial acceleration phase. The performance implications were staggering. A Bussard ramjet operating at full efficiency could, in theory, accelerate indefinitely. Given enough time, it could approach relativistic speeds. Physicist Carl Sagan described the concept enthusiastically. It appeared in science fiction across the following decades as the standard architecture for interstellar civilization. Engineers and physicists spent the following years working through the detailed calculations. The problems emerged systematically. First, interstellar hydrogen density. Early estimates used by Bussard assumed a density of hydrogen atoms in the interstellar medium that subsequent observations revised sharply downward. The actual average density is roughly 1 atom per cubic centimeter in some regions, and significantly less in others. At that density, the scoop required to collect sufficient hydrogen to power a fusion reactor would need to be hundreds of miles in diameter. Constructing and deploying a physical scoop of that size is beyond any foreseeable engineering capability. Second, the proposed fusion reaction. Bussard's original design specified proton-proton fusion, the reaction that powers stars. Proton-proton fusion is extraordinarily slow under laboratory conditions and requires temperatures and pressures that stars achieve through gravitational compression across millions of years. Replicating it in a reactor small enough to fly on a spacecraft has no demonstrated pathway. Third, and most decisive, a detailed analysis published in 1978 by physicists Bussard himself later acknowledged, showed that the electromagnetic scoop does drag. The process of collecting interstellar hydrogen through an electromagnetic field creates resistance opposing the spacecraft's motion. At the densities of hydrogen in interstellar space, the drag produced by a scoop large enough to collect meaningful fuel exceeds the thrust the fusion reactor can generate from that fuel. The ramjet decelerates while trying to accelerate. Updated analysis using modern measurements of interstellar hydrogen density confirms this finding. The Bussard ramjet, as originally designed, cannot achieve net positive acceleration in the actual interstellar medium. Modified versions have been proposed using different fusion reactions or scoop geometries. Some researchers suggest using the scoop only for braking at the destination, rather than acceleration. These modifications narrow the concept significantly. The ramjet as a general-purpose interstellar drive is no longer considered viable by the physics community. The concept lives in the same category as Project Orion, an idea with a real physical foundation, defeated by a specific calculation that reality delivered after the initial excitement. What that leaves, for crewed interstellar missions, is an engineering problem that no amount of propulsion improvement fully resolves. The crew must survive the journey, and keeping humans alive across decades of deep space transit inside a closed vessel is a systems challenge that begins failing at the human level long before the hardware does. If you cannot go fast enough to cross to another star in a single human lifetime, one architectural answer is to stop treating a single lifetime as the constraint. Build a vessel large enough, self-sustaining enough, and populated enough that the mission spans generations. The people who arrive were born on board. Their grandparents launched. Engineers and biologists have studied generation ship requirements seriously enough that detailed technical papers exist in peer-reviewed journals. The picture that emerges is one of compounding challenges at every level of system design. Start with population. Geneticists studying minimum viable populations for isolated groups calculate that avoiding harmful inbreeding over multiple centuries requires a founding population of several hundred individuals, at minimum, with some analyses pushing the number above 2,000 for true long-term genetic health across a centuries-long voyage. Each additional person adds mass requirements for food, water, air, living space, and waste processing. Closed-loop life support at the required scale is an unsolved engineering problem. The International Space Station recycles water and oxygen partially, but it receives regular resupply missions and relies on Earth for consumables that its systems cannot regenerate. A generation ship must close every loop completely. Food must be grown on board across sufficient agricultural area to feed the full population continuously for the entire voyage. Waste streams must be processed back into nutrients with near-perfect efficiency. A failure in any part of this system, with no resupply possible, is a survival emergency. Mechanical reliability over centuries is a materials and redundancy problem with no direct precedent. Every component that can fail will eventually fail, given sufficient time. A generation ship requires either redundant systems for everything critical or manufacturing capability on board to produce replacement parts from raw materials. A ship carrying a machine shop, raw feedstocks, and the engineering knowledge to rebuild its own systems is effectively a small industrial civilization traveling through space. The psychological dimension introduces a different category of failure mode. Studies from Antarctic winter overstations, submarine deployments, and isolated habitat simulations consistently show that long-duration confinement produces predictable psychological stress, social conflict, and leadership breakdown. These effects appear across cultures, across selection processes, and across varying levels of preparation. The longest continuous human isolation studies run to about a year and a half. A generation ship voyage to Alpha Centauri at currently achievable speeds would take tens of thousands of years. No study has examined isolation at that timescale, because no study can. The question of whether the crew's descendants, born into the ship with no memory of Earth, would maintain the mission's original objectives across centuries has no empirical answer. Cultural drift, institutional decay, and simple loss of technical knowledge are all documented in Earth-based historical civilizations operating under far less stress. Generation ships represent the most honest acknowledgement in mission architecture that the speed problem may not be solvable on human timescales, and they replace the speed problem with a complexity problem that may be equally insurmountable. The irony is that the Voyager probes, which cannot sustain human life and carry no crew, will outlast any generation ship as physical objects by orders of magnitude, while transmitting nothing useful within a few years. Voyager One and Voyager Two are, by any reasonable measure, the most enduring objects humanity has ever built. As physical hardware, they will likely survive for billions of years. In the cold vacuum of interstellar space, with no atmosphere to corrode them, no weather to erode them, and no significant collisions expected, the metal and electronics of both probes will persist long after Earth's oceans have boiled away, when our star expands in its final stages. The golden record aboard each probe, a gold-plated copper disc containing sounds, images, and greetings from Earth, was designed with exactly this permanence in mind. It is a message to whatever intelligence might eventually encounter the probe across an unimaginable span of time. The probe as a communicating, science-returning mission is a different story entirely. Voyager 1's power output has been dropping steadily since launch, as detailed in Chapter 16. Engineers have kept the probe scientifically productive by selectively shutting down heaters, instruments, and redundant systems, as power margins tightened. By the late 2020s, projections indicate power will drop below the threshold required to operate any science instruments at all. At that point, Voyager One becomes a silent artifact. It still exists. It still moves through interstellar space at 38,000 miles per hour. It carries its golden record. Its structure remains intact. But the mission, defined as collecting and transmitting data about the universe, ends. Voyager 2 faces the same timeline. Both probes will cross from functioning mission to silent monument within the same approximate window. The engineering lesson is stark. The most successful deep space mission in history, the probe that has traveled further from Earth than any human object ever built, has a science lifetime measured in decades and a physical lifetime measured in billions of years. The gap between those two numbers defines the core problem of interstellar mission design. Building something that lasts long enough to reach another star system is straightforward. Physics. Metal endures. Inertia is free. The probe will keep moving forever once launched. Building something that functions throughout that transit, that gathers and transmits meaningful data after travel times measured in thousands to tens of thousands of years, is a challenge for which no engineering tradition, no material science, and no electronics architecture currently provides a solution. Voyager 1's approaching silence is the universe's clearest demonstration of this principle, happening in real time, observable by anyone with access to the deep space network tracking data. The proposals that follow this dead end require either accepting silence and building probes that function only for the first decades of a very long journey, or finding a propulsion breakthrough that reduces transit time to something a spacecraft can survive. One such breakthrough, backed by a physicist with a serious mathematical framework, requires a form of space-time manipulation that current physics places in the category of theoretically permitted, but requiring something that may not exist anywhere in the observable universe. In 1994, a Mexican physicist named Miguel Alcubierre published a paper in a peer-reviewed journal proposing a method of faster-than-light travel that does not technically violate Einstein's theory of relativity. The concept works as follows. Relativity prohibits matter from moving through space-time faster than light. Alcubierre's proposal does not move the spacecraft through space-time. Instead, it contracts space-time in front of the spacecraft and expands it behind. The spacecraft sits inside a stable bubble of flat space-time. The bubble moves. Space itself moves around the spacecraft, carrying it toward the destination, without the spacecraft accelerating in the conventional sense. Inside the bubble, the crew experiences no acceleration forces. From their perspective, they are sitting still. From an outside observer's perspective, the bubble, and everything inside it, moves faster than light. The mathematics is internally consistent within general relativity's framework. The equations allow the solution. A warped bubble of the type Alcubierre described is a legitimate solution to Einstein's field equations. NASA's Advanced Propulsion Physics Laboratory, a small research group sometimes called the EagleWorks Lab at the Johnson Space Center, conducted funded research into Alcubierre's concept and related advanced propulsion ideas for several years. The research was real, the budget was small, and the goal was explicitly to determine whether any physical barriers existed that would definitively rule out the concept or reveal unexpected pathways forward. The barriers emerged. Alcubierre's original formulation required a quantity of negative energy, a form of energy with properties opposite to ordinary matter and energy, roughly equivalent in magnitude to the mass energy of a planet the size of Jupiter. Negative energy in small quantities has been observed as a quantum phenomenon, the Casimir effect, where two uncharged metal plates held very close together produce a measurable attractive force from vacuum energy fluctuations. The existence of negative energy in any form is confirmed. The existence of negative energy in Jupiter-scale quantities is firmly in the category of unknown and likely impossible given current physical understanding. Subsequent researchers worked on modified versions of the Alcubierre metric that reduce the exotic energy requirement. Published analyses have proposed geometries that lower the requirement substantially. Each reduction comes with its own set of unproven physical assumptions. A separate finding complicates the concept further. Analysis showed that the interior of a warp bubble, where the crew travels, would be causally disconnected from the bubble wall. The crew inside cannot send signals to the wall, meaning they cannot control or collapse the bubble from inside. A ship that cannot steer or stop itself once the bubble forms is not a useful vehicle. The Eagle Works research concluded without a breakthrough. The physical barriers identified, particularly the exotic matter requirement, remain unresolved in published literature. The warp drive sits where it has sat since 1994, mathematically permitted, physically requiring something that may not exist, and practically distant from any engineering realization. What researchers examining the problem from a more constrained perspective concluded is that the fastest credible path to another star system may require sending something so small that the mass ratio problem essentially disappears. Every propulsion problem examined so far scales with mass. The rocket equation punishes heavy spacecraft. The laser array required for breakthrough starshot scales with the sail area needed to push a given mass. Radiation shielding adds mass to protect mass. Life support mass protects human mass. The entire engineering structure of interstellar travel becomes progressively more tractable as the payload shrinks. Take that logic to its extreme conclusion, and you arrive at the wafersat concept, a spacecraft the mass of a paperclip or smaller, built on a single thin chip containing a camera, spectrometer, communication system, and power source. Breakthrough Starshot's baseline design targets a payload of roughly 1 gram. The sail that carries it, called a light sail, would be a few meters wide but nanometers thick, made of advanced metamaterials with high reflectivity and low mass. The total spacecraft, sail and payload combined, would mass a few grams at most. At that mass, the laser array calculations become physically conceivable, though still enormously challenging. The erosion problem from Chapter 10 still applies, but a sacrificial ablation layer on a gram-scale craft can be designed into the mass budget more easily than on a large vehicle. The power requirements for communication home remain a serious challenge, but miniaturized laser transmitters and large receiving arrays on Earth offer a pathway. Several research groups worldwide are actively developing the component technologies. Miniaturized cameras, spectrometers, and communication systems have advanced dramatically in the last 2 decades. Driven by the CubeSat industry, chips smaller than a fingernail now carry computational power that filled rooms in the 1980s. The gap between current miniaturization capability and a functional gram-scale interstellar probe is real, but not infinite. Engineers can describe what components are needed. Some of those components exist in early prototype form. The fundamental trade-off is scientific return. A gram-scale probe flying past Alpha Centauri at 20% of light speed for a few hours collects a fraction of the data that a larger, slower orbiting mission would gather. Images would be limited in resolution. Atmospheric analysis of any planets encountered would be basic. The communication bandwidth across 4 light-years from a gram-scale transmitter would be extremely low, meaning data transfer rates slow enough that transmitting a single high-resolution image could take years. Mission designers at Breakthrough Starshot have acknowledged this openly. The first generation of such probes would confirm whether planets in the Alpha Centauri system exist and have basic physical characteristics. That information alone would be transformative. It would not answer whether those planets are habitable or inhabited. For that level of investigation, a larger, slower mission architecture with braking capability would eventually be required. And a larger mission architecture reintroduces every mass and propulsion problem in the preceding chapters. Miniaturization is a genuine partial solution. It is the most credible near-term pathway to getting any human-built object to another star. And it still faces hardware that doesn't exist, a laser array that would be the largest ground installation ever built, and a mission that cannot stop at its destination. Stopping requires a crew that can make decisions on board. And what happens to that crew, psychologically over a multi-decade voyage in a sealed environment, has been studied, quietly and systematically, through the most extreme isolated environments humans currently occupy. The longest continuous human spaceflight record belongs to Russian cosmonaut Valery Polyakov, who spent 437 consecutive days aboard the Mir space station. He landed, walked without assistance, and recovered. The experiment demonstrated human physical resilience at timescales relevant to a Mars mission, A crewed interstellar mission would last 40 years at minimum, assuming propulsion technology not yet available. The psychological research relevant to such a mission comes from the most extreme analogues humans currently experience: Antarctic winter overstations, nuclear submarine deployments, and isolation habitat simulations. The findings across these environments are consistent enough to be called a pattern. Social dynamics inside isolated small groups follow a predictable arc. Initial cohesion, a period researchers call the third quarter phenomenon, where morale drops sharply past the halfway point, followed by either recovery or progressive fragmentation as the end approaches. The third quarter effect has been documented across Antarctic missions, submarine tours, and long-duration space simulations, including the Mars 500 study, a 520-day simulated Mars mission in Moscow. Leadership becomes a source of conflict rather than stability in roughly half of long-duration isolation studies. Authority structures designed before the mission struggle to adapt to conditions that arise inside the habitat. Formal hierarchies compete with informal ones that form organically under stress. Sensory monotony produces measurable psychological effects. The same walls, the same people, the same sounds, the same tasks for years on end generates a documented condition called chronic mild stress, which degrades decision-making, increases irritability, and reduces creative problem-solving capacity progressively over time. Researchers studying crew psychology for Mars missions, which would last 1 to 3 years, have identified cognitive fatigue as one of the primary unresolved challenges. A crew must remain cognitively sharp enough to handle emergencies, conduct scientific work, and make sound judgments across the entire mission duration. Sustained cognitive performance under monotony and isolation degrades in ways that physical training and selection cannot fully prevent. For a 40-year interstellar mission, these timescales multiply by factors of 15 to 40 compared to Mars. The psychological literature contains no data for isolation of that duration, because no study has approached it. The closest analog is multi-generational transmission of community identity and purpose in isolated historical communities, such as island populations or remote settlements cut off from outside contact. Those examples show that cultural and institutional drift over 2 to 3 generations is essentially universal. Knowledge decays, priorities shift. The founding mission loses its grip on people who had no role in choosing it. Mission designers who take these findings seriously reach a consistent conclusion. A 40-year crewed interstellar mission is a psychological challenge of the same order of magnitude as the engineering challenges. And unlike the engineering problems, no amount of materials research or power generation improvement addresses it. Biology itself becomes the final constraint, and the radiation environment, the isolation, and the closed ecosystem all press on the crew's bodies in directions that even the best preparation cannot fully counter. The stars the crew is flying towards bring their own radiation problem that begins the moment any spacecraft crosses into the destination system. Every star produces a stellar wind, a continuous outflow of charged particles streaming outward in all directions, filling a bubble of space around the star the way our own star fills the heliosphere. A spacecraft arriving at another star system after decades of interstellar transit doesn't enter calm space. It enters a new star's radiation environment, one that the crew and instruments have no protection against, because the spacecraft carries none of the magnetic field shielding that planets with active cores generate naturally. The heliosphere that surrounds our solar system shields the inner planets from the harshest interstellar radiation. A planet in another star system sits inside its own star's equivalent bubble and may receive protection from its own magnetosphere. A spacecraft, flying without a planetary magnetosphere, enters the stellar wind zone essentially bare. The severity of this arrival environment depends on the destination star's type and activity level. Alpha Centauri consists of 3 stellar bodies. The 2 largest are Sun-like stars, relatively stable by stellar standards. The third, Proxima Centauri, is a red dwarf and the closest individual star to our solar system, at 4.2 light-years. Proxima Centauri's stellar wind is a serious problem. Red dwarf stars are smaller and cooler than our star, but they are magnetically violent. Proxima Centauri produces stellar flares, intense bursts of radiation, and charged particles, with a frequency and intensity that dramatically exceeds our star's flare activity. Studies of Proxima's flare record show major flare events occurring multiple times per year. During a flare, radiation levels in the surrounding region spike sharply. A spacecraft arriving at Proxima Centauri at the moment of a major flare would receive a radiation dose that current shielding concepts could not fully mitigate. The timing of arrival is not controllable from a launch 40 years prior. The planet designated Proxima b, confirmed to exist within Proxima Centauri's habitable zone, sits close enough to its star that the stellar wind it receives is estimated to be roughly 2,000 times the intensity our planet receives from our star. Any atmosphere it possesses is being actively eroded by that wind. For a spacecraft attempting to orbit or approach Proxima b, the operational radiation environment during a flare represents a systems and crew safety challenge with no current engineering solution. The targeting challenge compounds this. A spacecraft aimed at a star 4 light-years away, with a launch to arrival time of 40 years, must account for the motion of the destination star through the galaxy during that transit. Stars move. Proxima Centauri's trajectory is known well enough to calculate, but any small error in the launch trajectory compounds across 4 light-years of travel. The margin for targeting error at interstellar distances is smaller than any guidance system ever built for a spacecraft has needed to achieve. When an engineer plans a mission to Mars, trajectory corrections happen continuously. The spacecraft launches on an approximate course. As it travels, ground teams measure its actual position against the intended one and fire small thrusters to correct the difference. Multiple correction burns happen over months. The spacecraft arrives within its intended target zone. Across interstellar distances, this approach fails. At the speed of light, a signal from Earth to a spacecraft at Alpha Centauri takes 4.2 years. A command to fire a correction thruster arrives 4.2 years after it was sent. The spacecraft's response takes another 4.2 years to confirm. A correction identified today takes over 8 years to execute and verify. For a spacecraft traveling at 20% of light speed, the crossing takes roughly 20 years. The window for meaningful trajectory correction from Earth is extremely narrow at the beginning of the journey, and functionally closed for most of it. This means launch accuracy must be extraordinary. Interstellar navigation requires pointing a spacecraft from Earth at a target 4 light-years away with an angular precision so fine that any error maintained across the entire transit still results in the spacecraft passing through the target system rather than missing it entirely. The destination star's gravity becomes a targeting aid as the spacecraft approaches. If the trajectory is close enough, gravitational attraction from the destination star will pull the probe onto a flyby or orbital path, but close enough still means arriving within a manageable distance after 4 light-years of travel. A pointing error of 1/1,000,000 of a degree at launch, compounded across 4.2 light-years, produces a positional error of roughly 50 million miles at the destination. 50 million miles is roughly the distance from Earth to Venus at closest approach. A spacecraft missing its target by 50 million miles flies past the destination system entirely, unable to correct, on a trajectory into deep interstellar space with no second chance. Current precision guidance systems for deep space missions work at much shorter ranges. The pointing accuracy required for an interstellar trajectory represents an improvement beyond anything operationally tested. Additionally, stellar positions as observed from Earth show the star where it was years ago, when the light we see left it. For a star 4 light-years away, we see it as it was 4 years in the past. Its current position requires calculation based on known proper motion, the star's movement across the sky over time. Any unmeasured component of that motion introduces targeting error. Researchers working on breakthrough starshot have identified the targeting requirement as one of the most technically demanding aspects of the mission, comparable in difficulty to the laser array itself. A spacecraft that threads the targeting needle, survives the interstellar erosion, crosses the radiation environment of the destination system, and arrives at its target still has the problem of slowing down. As established in Chapter 12, slowing down may be harder than everything that came before it. And even if it arrives functional, the data it collects must be transmitted across 4 light-years to instruments on Earth sensitive enough to receive it. Everything depends on the probe surviving the arrival intact. One proposal that could keep a human crew biologically intact for multi-decade transits has been studied seriously since the 1980s, and it draws its credibility from animals that already do a version of it every winter. Certain ground squirrels in North America reduce their core body temperature during hibernation to within a few degrees of freezing. Their heart rate drops from roughly 200 beats per minute to fewer than 10. Their metabolism slows to roughly 1 to 5% of normal levels. They remain in this state for months, wake on their own, and show no lasting neurological damage. This is confirmed biology, documented across multiple species. Larger mammals hibernate differently. Bears drop their body temperature by only a few degrees and cycle in and out of deeper sleep states, rather than entering the profound metabolic suspension of ground squirrels. The mechanisms underlying true deep hibernation, the biochemical signals that prevent ice crystal formation in cells, the processes that suppress metabolism without causing organ failure, are active research areas in medicine. The appeal of hibernation for crewed spaceflight is straightforward. A crew in metabolic suspension consumes dramatically less food, water, and oxygen. The psychological isolation problem diminishes substantially if crew members are unconscious for most of the transit. Radiation exposure accumulates more slowly in cells with depressed metabolic activity, though the cosmic ray particle bombardment continues regardless of the recipient's wakefulness. NASA's Human Research Program has funded investigation into torpor induction for spaceflight applications. A team led by biomedical engineer John Bradford developed a concept for a torpor habitat for Mars missions that would cycle crew through periods of metabolic suppression, using a combination of cooling and intravenous nutrition. The concept received Phase 2 study funding from NASA's Innovative Advanced Concepts program. The critical distinction between studied proposals and science fiction is the depth of torpor involved. Current medical capability can induce mild hypothermia in patients for therapeutic purposes, used in some cardiac surgeries, with core temperatures reduced to around 68 degrees Fahrenheit for a matter of hours. Recovery is well documented at this level, reducing human core temperature to near freezing for weeks or months, the level required for meaningful metabolic suspension over a multi-year transit, has no clinical precedent. The barrier is ice crystal formation in cells and tissues. Below a certain temperature threshold, water in biological tissue begins forming ice crystals that puncture cell membranes. Cryoprotectant chemicals, which are compounds that lower the freezing point of biological tissue, have been used successfully to preserve organ tissue for transplant and to freeze embryos for fertility treatments. Scaling cryoprotection to an entire human body, delivering sufficient concentrations to every tissue, and reversing the process without toxic accumulation is a problem that has defeated every attempt at full body preservation to date. The research is advancing. Certain tissues and small organisms have been successfully vitrified, meaning cooled without ice formation, and revived. The gap between preserving a small organism and preserving a human nervous system is enormous and currently uncrossed. For a 40-year interstellar transit, even partial torpor induction, cycles of weeks in suspension and weeks awake would be transformative for crew health and resource consumption. Full suspension for the entire voyage remains in the category of biological aspiration, backed by incomplete but advancing science. The ship carrying that crew would face its own survival challenge independent of the biology. A structure designed for multi-decade spaceflight must remain sealed, pressurized, and mechanically functional for timescales that test every material and seal humanity has ever manufactured. Deep space is cold. Far from any star, ambient temperatures drop to just a few degrees above absolute zero, roughly minus 455 degrees Fahrenheit. At these temperatures, the behavior of materials changes in ways that engineers must account for carefully. Most metals become brittle at cryogenic temperatures. The ductility that allows metal to bend before breaking, which protects structures from fracture under stress, decreases as temperature drops. Steel alloys commonly used in engineering applications can experience dramatic reductions in impact resistance at deep space temperatures. A component that flexes safely at room temperature may fracture under the same load at cryogenic temperatures. Spacecraft engineers address this through material selection. Aluminum alloys and certain stainless steel compositions maintain reasonable toughness at low temperatures. Titanium performs well across wide temperature ranges. The materials for deep space vehicles are chosen with these properties in mind. For missions measured in decades, thermal cycling introduces a separate challenge. Every component that transitions between temperature extremes repeatedly, such as a spacecraft passing in and out of sunlight in the inner solar system, before heading into deep cold, experiences thermal stress as different materials expand and contract at different rates. Repeated cycling fatigues materials at joints and interfaces. Seals crack, bonds weaken. The effect accumulates. For a spacecraft spending decades at stable cryogenic temperatures in true interstellar space, thermal cycling ceases after the vehicle leaves the inner solar system. The structural challenge shifts to long-term creep and radiation damage to materials. Polymers, which include the seals, gaskets, and insulating materials essential to spacecraft systems, degrade under prolonged radiation exposure. Polymer chains break, changing mechanical properties. Seals become brittle. Insulation loses effectiveness. The timeline for significant polymer degradation in the deep space radiation environment, considering galactic cosmic ray flux, is measured in decades. O-ring seals on pressurized systems would require replacement or redesign for multi-decade missions. Replacing an O-ring in a pressurized habitat during an interstellar voyage requires both spare parts and the ability to perform the maintenance without external support. The electronic situation is more complex. Radiation-hardened electronics are designed to tolerate accumulated radiation doses, measured in total ionizing dose. The galactic cosmic ray environment delivers dose at a slower rate than near-Earth radiation belts. But across 40 years of transit, accumulated dose reaches levels that exceed the specified tolerance of many current radiation-hardened components. Researchers studying multi-decade mission architectures propose designs using redundant systems with periodic rotation, where primary systems go dormant and backup systems take over, allowing the primary to partially recover before its next active cycle. This approach extends operational life but requires the redundant systems themselves to survive the same radiation environment. A spacecraft designed to function for 100 years in interstellar space does not exist as a current engineering artifact. The system's heritage from which such a design would draw, meaning vehicles with documented performance data across comparable timescales and environments, is empty. Voyager One, at roughly 50 years, represents the longest deep space operational record, and it is approaching failure. One concept that sidesteps materials longevity by embracing relativistic physics proposes turning time dilation from a curiosity into a survival mechanism. At the velocities required, the crew ages more slowly than the universe around them. But what they return to, if they return, is a civilization that has aged by centuries. Einstein's special relativity contains a consequence that most people know by name and few appreciate in engineering terms. As an object accelerates toward the speed of light, time for that object passes more slowly relative to a stationary observer. At 10% of light speed, the effect is small but measurable. At 90% of light speed, the effect is dramatic. At 99% of light speed, 1 year aboard the spacecraft corresponds to roughly 7 years in the outside universe. At speeds approaching within fractions of a percent of light speed, the ratio becomes extreme. A spacecraft accelerating at 1 gravity, comfortable for a crew, 1 gravity being the acceleration that mimics Earth's surface gravity, would reach Alpha Centauri in what feels like about 3.6 years to the crew. Meanwhile, roughly 4.4 years pass on Earth. The difference at that modest distance is small. Apply the same 1 gravity acceleration to a journey across the galaxy, roughly 100,000 light-years. The crew experiences about 12 years of shipboard time. The universe outside experiences 100,000 years. A ship that returns from such a voyage comes back to a civilization 100,000 years older than the one that launched it, assuming human civilization persists at all. The crew members are 12 years older. Everyone they knew is gone by geological timescales. Science fiction writer Paul Anderson explored this concept in a 1970 novel that gave this flight profile its informal name, the Tau Zero scenario. The engineering version is called a Bussard ramjet in the original story, but the relativistic time dilation is the actual scientific content of the concept. For mission designers, relativistic time dilation offers a genuine biological solution to the crew longevity problem. If a spacecraft can sustain acceleration close enough to light speed, the crew survives the journey in calendar years rather than centuries. The transit becomes a human-scale experience. The cost is absolute severance from the civilization that launched the mission. Crew members who depart in 2025 and arrive at their destination after 10 years of shipboard time step out into a world, or a star system, that is 10 to 100,000 years past their departure date, depending on their speed. Communication with Earth during the voyage arrives with increasing delay. Return communication from Earth falls further and further behind. By the time the crew has traveled at 99% of light speed for a year, messages they receive from Earth were sent 7 years ago. By the time they decelerate and look back, Earth's current moment is decades in their ship's past and unreachable in any conversational sense. The practical engineering requirement for this scenario is sustained propulsion at a significant fraction of light speed for years. Every propulsion concept examined in previous chapters fails this requirement either on fuel mass, power availability, or physical material limits. Relativistic time dilation is a real physical phenomenon confirmed by precision atomic clocks on aircraft and satellites. The technology to exploit it for crewed interstellar travel does not exist. And the loneliest aspect of the mission planning picture is this: the civilization that might eventually develop the required propulsion might choose to send machines rather than crews. Machines that can replicate themselves, build infrastructure at the destination, and return information without any of the biological constraints that make crewed missions so difficult. Hungarian-American mathematician John von Neumann described the concept of a self-replicating machine in the 1940s as a theoretical exercise in computation and automata. A machine that contains instructions for building a copy of itself, gathers raw materials from its environment, and constructs a functional duplicate could in principle spread indefinitely given sufficient time and resources. Applied to interstellar exploration, the concept becomes a von Neumann probe, a spacecraft that travels to another star system, locates raw materials in that system, builds copies of itself using those materials, and sends the copies onward to further star systems. Each generation of probes builds the next. The network expands exponentially. The physics of this concept contains no known barrier. Material science, automation, and manufacturing are engineering challenges, not fundamental physical limits. A sufficiently advanced civilization with sufficiently capable manufacturing technology could, in principle, build such a probe. The exploration implications are staggering. A single von Neumann probe launched from Earth, over timescales of millions of years, could fill the entire galaxy with its descendants. Every star system within range becomes accessible to the probe network, without requiring humanity to solve crude spaceflight, antimatter production, or any of the fundamental propulsion challenges discussed in this mission brief. This is why the concept is taken seriously by researchers in both the engineering and astrobiology communities. The engineering requirements, while formidable, are directional. The probe must carry a complete manufacturing system capable of operating on raw, asteroid or planetary materials at the destination. It must carry a complete copy of its own design specifications. It must carry sufficient artificial intelligence to direct resource acquisition, manufacturing, and launch of copies without Earth supervision. And it must carry a power system adequate to run all of those functions. No current technology meets any of these requirements in the form needed for interstellar application. Terrestrial manufacturing automation, miniaturized artificial intelligence, and compact nuclear power sources are all advancing. The gap between current capability and a functional self-replicating interstellar probe is measured in generations of engineering progress, not fundamental physical barriers. The philosophical dimension of von Neumann probes generates debate outside the engineering community. A self-replicating machine, sent to foreign star systems, operates autonomously for millions of years, makes decisions without human oversight, and transforms materials and systems that may contain life or intelligence. The question of what values and constraints such a machine should carry, and whether those constraints would survive millions of years of operation and replication, has no agreed answer. Some researchers have pointed to von Neumann probe logic as one possible resolution to the Fermi paradox. If any civilization has built such probes, the galaxy should already be full of them. The absence of detected probes either means no civilization has reached that capability, or the probes are here and we haven't recognized them, or some property of the physics or engineering makes the concept consistently fail in practice. That silence is the most unsettling data point in all of interstellar exploration research, and it connects directly to the next problem. Every mission we could launch would arrive at a destination chosen based on observations that are years, decades, or centuries out of date. The information we have about every star, every planet, every possible destination outside our solar system is old. Light from Alpha Centauri takes 4.2 years to reach Earth. The images we have of its companion stars, the spectroscopic measurements of their atmospheres, the radial velocity data used to detect planets, all of it depicts those objects as they existed 4.2 years ago. For stars further away, the lag is proportionally longer. The star system 60 light-years from Earth, that exoplanet surveys are studying now, shows us conditions as they existed 60 years ago. A mission launched toward that system at 10% of light speed, arriving 600 years from now, would be targeting a destination based on observations from 6 centuries in the past. Stars change. Planetary systems evolve. A planet with a stable atmosphere today may have lost it to stellar activity in 400 years. A star in a quiet phase now may enter an active period before a spacecraft arrives. The targeting decision made at launch is a bet on conditions that cannot be confirmed until the probe arrives, at which point communication back to Earth takes as long as the one-way light travel time. For the nearest stars, this lag is manageable. 4 years of observational uncertainty for Alpha Centauri is a relatively small margin when the mission takes 40 years and the destination is confirmed to have at least one planet in the habitable zone. For more ambitious targets, the problem compounds. Interstellar mission advocates often propose targeting systems with confirmed Earth-like planets in habitable zones. But confirming habitability, meaning surface liquid water, stable atmospheric chemistry, and absence of hostile stellar activity, requires observations over decades. The exoplanet detection methods currently used, transit photometry and radial velocity measurement, confirm a planet's orbital period and approximate size. They do not confirm surface conditions. A mission aimed at a planet showing biosignatures, chemical indicators of biological activity, faces the additional uncertainty that by the time the probe arrives, the biosignatures may reflect conditions that existed centuries ago. Life on such a planet may have changed dramatically, or the signatures may have been misinterpreted entirely. Mission designers working seriously on interstellar concepts acknowledge this uncertainty explicitly. The first interstellar missions would be reconnaissance by necessity, flying fast, collecting brief data, and transmitting it back to inform decisions about follow-up missions launched years or decades later. The gap between what we can observe from Earth and what actually exists at a destination light-years away will remain until we have real-time communication across interstellar distances. And real-time communication requires either a physical relay network in interstellar space or a communication technology faster than light, neither of which currently exists. Every interstellar target is a historical photograph, not a live feed. The mission planning community builds around that constraint, knowing the first crew or probe to arrive will encounter conditions last observed years before they launched and never updated since. That observation delay is itself one possible answer to a question that has haunted astronomy since the 1950s. A question about why, if interstellar travel is possible and intelligent life exists elsewhere, the galaxy seems so quiet. In 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation drifted to the possibility of intelligent life elsewhere in the galaxy. Fermi thought for a moment and asked a question that has not been satisfactorily answered since. Where is everybody? The galaxy contains roughly 400 billion years old. Our own civilization developed technological capability within a few thousand years of becoming biologically modern, a blink in cosmic time. A civilization that formed just a few million years earlier than ours, a tiny fraction of the galaxy's age, would have had time to colonize every star system in the Milky Way many times over, even at speeds far below light speed. The galaxy should be full. Signals should be detectable. Von Neumann probes should have arrived here long ago. And yet, after decades of systematic searches, no confirmed signal, no detected probe, no unambiguous artifact of another technological civilization has been found. This is the Fermi paradox. Its relevance to interstellar engineering is direct. Every engineering barrier examined across this mission brief represents a potential answer to Fermi's question. If chemical propulsion's ceiling, the rocket equation's tyranny, the energy requirements for meaningful velocity, the radiation environment, the power decay, the materials degradation, and the deceleration problem all stack together into a barrier that no civilization can consistently overcome, the silence makes sense. Interstellar travel is not prohibited by physics. The Alcubierre mathematics works. Antimatter's energy density is real. But the engineering gap between knowing the physics and building the infrastructure may be so wide that civilizations consistently exhaust themselves, destroy themselves, or redirect their efforts before crossing it. Some researchers call this the Great Filter, a barrier in the development of any civilization that most do not survive or surpass. The question is whether the filter lies behind us, meaning humanity has already passed the hardest part, or ahead of us, meaning the most difficult challenge is still coming. Interstellar engineering, viewed through the lens of the Fermi paradox, suggests a sobering possibility. The universe may be filled with civilizations that developed technology, calculated the distances, ran the engineering numbers on every propulsion concept, built the most capable probes their physics allowed, and found themselves exactly where we are. In possession of a machine moving at 38,000 miles per hour toward the edge of a solar system, it will not clear for 30,000 years. The silence of the galaxy may be the most honest engineering review ever conducted, and it makes the one proposal that engineers consistently identify as the most credible first real step, the step that hasn't been taken, the one that would actually advance the mission, feel both more urgent and more frustrating than anything else in this brief. After every wall examined, every engineering dead-end catalogued, and every physical constraint confirmed, a consistent answer emerges from the small community of researchers who work on interstellar mission concepts professionally. The first step is a dedicated interstellar precursor probe. The concept is specific, and the engineering is grounded. A mission designed not to reach another star system, but to study the interstellar medium in depth, to characterize the radiation environment beyond the heliopause, to test propulsion technologies in actual interstellar space, and to demonstrate the communication and power systems required for longer missions. A precursor probe would travel to roughly 200 to 1,000 astronomical units from our star, well into the region Voyager One is crossing now. But with modern instruments and systems designed for the specific science of interstellar space, it would measure the density and composition of the interstellar medium directly, not inferred from distant observations. It would characterize the galactic cosmic ray environment across the heliopause transition. It would test advanced radioisotope or nuclear fission power systems at the power levels required for future longer missions. Proposals for such a mission have been formally submitted to NASA, the European Space Agency, and various national science foundations multiple times across the last 3 decades. A serious study called the Interstellar Probe Concept, developed by a science team at Johns Hopkins Applied Physics Laboratory, was submitted to the most recent Planetary Science Decadal Survey, the major document that shapes NASA's mission priorities for a decade at a time. The study was detailed, technically grounded, and identified a launch window using a combination of an advanced solar Oberth maneuver and a large launch vehicle that could place a probe on a trajectory 3 to 5 times faster than Voyager One. The mission cost estimate was roughly $10 billion over 30 years, comparable to flagship planetary science missions like Cassini or the Hubble Space Telescope. The decadal survey acknowledged the science value of the concept. Funding was not allocated. The mission priority ranking placed it below other planetary science objectives. The interstellar precursor probe remains unbuilt. The researchers who study this problem describe the funding gap with a specific frustration. Every other category of space science, planetary science, astrophysics, heliophysics, has a funded mission cadence. Missions launch on decade-scale schedules. Interstellar Science has 2 probes launched in the 1970s that were designed for planetary flybys and are currently approaching instrument failure. The engineering required to send a dedicated probe to interstellar space with modern instruments and a 30-year operational lifetime is within reach of current technology. The propulsion improvements needed are incremental, not revolutionary. The science return would directly address every uncertainty that makes deeper interstellar mission planning speculative. The mission doesn't exist because the political and institutional framework for funding it doesn't exist. Interstellar science occupies a gap between planetary science, which owns missions inside the solar system, and astrophysics, which observes the universe from Earth orbit or nearby. A mission that leaves the solar system permanently to study the medium between stars falls between those institutional categories. This is the real reason no spacecraft has left our solar system in a scientifically meaningful sense. Physics has not stopped us. Engineering has not stopped us. A mathematical formula from 1893 has not stopped us. The rocket equation is a challenge, not a verdict. What has stopped us is the absence of a sustained, funded, institutionalized commitment to the problem. Every mission that has approached the edge of our solar system has done so as a byproduct of planetary science objectives. The edge itself has never been the mission. Voyager One flies on. 38,000 miles per hour. Instruments fading. Power dropping. Carrying a golden record addressed to whoever finds it billions of years from now, in a direction no second spacecraft is following. The distance to the nearest star remains the same as it was when Tsiolkovsky wrote his equation. We know exactly why. We know exactly what it would take. The mission is waiting for the decision to begin.